Let us take on the next example problem. This is also pertaining to impulse momentum, but in an angular sense to start with. So, we want to see if we have a thin hoop and if it slips during the depicted interval. So, the thin hoop starts at this end A, and an initial moment which scales as the time 2t cubed over 3 is the initial moment acting on the hoop, and this moment causes the hoop to roll from left to right. We are told that it reaches a point B some distance away at a time Tf equals 9 seconds. We are asked to find the final velocity, and we are asked to determine if the hoop would have slipped in this interim time. Okay, so, the only way to find if a hoop slips is to calculate the friction force necessary to keep the hoop from slipping, and then compare that necessary friction force to the maximum possible friction force that is available. Okay, so, let us do that calculation. So, first of all, I draw a free body diagram of the hoop. There is a normal reaction, there is a moment m that acts on it, we are told there is a friction force F, this is the center of mass of the hoop. There is a weight W that acts through the center of mass. This completes our free body diagram. So, now for the kinetics of this problem, kinematics, if the angular acceleration is alpha and if the linear acceleration is A, then A equals R alpha. This is what the kinematic relationship would tell us. So, this implies A equals 2 alpha, R equals 2 meters in this particular problem. Okay, so let us take our free body diagram and apply Euler's first law. If I take all forces to the right being positive, that says minus F equals m times A, which implies minus F equals is equal to 2 m alpha. I will call this our first equation. Now, taking clockwise moments positive, the only set of forces that cause a moment, the only force in fact that causes a moment is F, and that causes a moment F times R plus m equals Ig times alpha. Like always, this is written in the frame of reference with the center of mass being the reference point. So, this says 2F plus m equals mr squared alpha. M is a known moment. Or a couple that is acting on this body. So, I will substitute equation 1 into equation 2. That says F equals minus 2 m alpha. So, this is minus 4 m alpha plus m equals 4 m alpha, r being 2. So, m equals 8 m alpha, which implies alpha equals m over 8 m. M is the mass of the hoop itself. So, now F is minus 2 m alpha minus 2 m times alpha is capital M over 8 m. F is minus m over 4. So, I want to draw our first observation from here. For any m, in fact, I will generalize this and say that f of t can be a time varying friction force, because m of t is a time varying moment acting on the hoop, and this f of t is simply proportional to m of t. Now, what I do know is that f max equals mu times n. It cannot, f of t cannot exceed mu times n. So, which also implies f max equals mu, in this case we are told is 3 over 8, and n would simply be equal to w, n is 96 newtons. So, this is 3 over 8 into 96. So, F max is 36 Newton. So, the maximum possible friction force is 36 newtons. So, let us see what the implications of this are. So, the first thing we see is that if m is clockwise, F acts from left to right, not right to left as we had assumed. Go back to our free body diagram. I assumed F is acting to my left, right? But in reality we found that if m is clockwise, F is actually negative, which means it is acting from right to left, from left to right, which means that this is similar to your front wheel in the car. If the front wheel, if the engine produces a torque of magnitude m, then the friction between the road and the tire, so if this was a road and this is a tire, the friction force would actually provide traction to move the car in a forward sense. Okay. But as far as F max is concerned, this sign, negative sign, does not matter. What I do know is that if the magnitude exceeds F max, this F of t is the magnitude of the friction force required for no slip. If this magnitude exceeded F max, then we know the hoop will slip. The magnitude acting is 2t cubed over 3. So, let us plug that in there. So, 2t cubed over 3 times 4 is greater than 36 newtons. Whenever this condition is achieved, the hoop is likely to slip. So, if I take care of this calculation, so whenever Tf cubed is greater than which implies if Tf is greater than 6 seconds, the hoop will slip. Okay, so let us go back to this problem. So, we found that whenever that at this instant 6 seconds, the magnitude of the friction force required for no slip will exceed the maximum possible friction force, which is mu times n. So, let us see what that looks like. So, we are told that the total span of time over which the motion is being analyzed is 9 seconds. So, up until 6 seconds in this span of time there is no slip. Beyond that, for the 3 seconds, from 6 seconds to 9 seconds, the hoop will slip. Okay, so we have two motion configurations happening in this span of 9 seconds, and we will need to analyze the two separately. So, let us first do the calculation for the no slip part. So, under no slip, what we do know is that F is that alpha equals m over 8m m for this hoop is 9.6 kg. T cubed over 12 m radian per second squared. So, if I integrate this from 0 to 6 seconds and knowing that the linear acceleration is 2 alpha so this is v at 6 seconds would be equal to this. More specifically, v at 6 seconds minus v at 0 seconds equal to this, but v at 0 seconds is known to be 0. This is 0 to 6, twice alpha is t cubed over 6m dt . So, this is 36 into 36 by 24 m . So, I am going just for the sake of simplicity, I am going to assume m is 9.6 kilograms. Or to make it simple, I am going to assume m is 10 kilogram because it really is not going to make much of a difference, which implies velocity at 6 seconds is 5.4 meters per second. This is the linear velocity. The angular velocity is equal to alpha at 6 seconds. Alpha was essentially I have to do the same integration from 0 to 6 seconds alpha dt. If I need to find the angular velocity, that is the way I would do it. Now, from 6 seconds to 9 seconds, the hoop is slipping, we do know that. So, the previous free body diagram we drew would no longer be valid. For this case, what we need to do is that the same moment m is acting, the rest of the free body diagram is unaltered, except now the friction force acting to move this forward is equal to F max. So, in other words, this counteracting moment m has exceeded the value that is below which it needs to stay for the friction force to cause no slip at the point of contact B. So, for all other points, the traction force between the tire and the road takes on the maximum value of the friction possible, which we calculated to be 36 newtons. So, now if I take the free body diagram, there is no kinematic relationship between A and alpha. So, the linear acceleration and the angular acceleration for this instance are no longer coupled. The angular acceleration is whatever is caused by the moment turning the wheel, turning the shaft, and the linear acceleration is whatever the traction force F can sustain. So, let us apply our laws of motion. Sum of forces equals mass times acceleration. I am going to assume m is 10 kg. So, if 36 Newton is the force acting, so A is 3.6 meters per second squared. This is the linear acceleration for the duration that the hoop is slipping at the point B. Now, we do know that if I integrate this acceleration, although this is not time varying, I am going to generalize this equation and say, if I perform an integration of this acceleration from time duration 6 seconds to 9 seconds, that gives me the total change in the velocity between the final instant 9 seconds and the instant 6 seconds. We already know the velocity at 6 seconds. So, if I is V of 9 minus 5.4, which also implies that the velocity at 9 seconds is 10.8 plus 5.4, which is 16.2 meters per second. So, the final velocity at 9 seconds is 16.2 meters per second. So, let us go back and quickly recap here. We encountered two separate situations for the duration from 0 to 6 seconds. The hoop was rolling under no slip. So, this is like you are at a traffic light, your engine exerts a torque on the shaft, and that torque itself, let us say, was time varying, okay, with m of t being 2t cubed over 3. Initially, since the torque itself is quite small, there is no slip, but as the torque increases, as the moment increases, at a time instant of 6 seconds, the traction force between the tire or the hoop and the road reached a point where it could no longer sustain motion under no slip, and at that point essentially the hoop started to slip. So, the first instance is analyzing motion under no slip, and then from 6 seconds to 9 seconds the hoop is now slipping, which means the traction force is the maximum possible, which is 36 newtons, and under that condition I get an acceleration of 3.6 meters per second squared. The end result is motion under no slip. So, this 5.4 meters per second of velocity was acquired under no slip conditions, and an additional 10.8 meters per second was acquired under slipping conditions, and the actual velocity of the hoop at 9 seconds is 16.2 meters per second. So, this tells us how to analyze motion when you have two separate situations happening, a part of time when slip was not happening and then a subsequent part of time when slip was happening. And in order to determine whether slip happens, the only way to get there is to first solve the no slip problem, understand the magnitude of the friction force needed to sustain motion under no slip, and check if you have that much friction. Once you have checked whether you have friction, you can then move into the phase where you analyze the problem into two halves, one where the hoop was rolling under no slip and a second where the hoop was rolling under slip conditions. So, we will now continue this discussion with our next example problem.